I'm pleased to introduce the last speaker in our session, Rebecca Bilbro, who is the lead data scientist at ByteCubed, and she's an emeritus member of the local DC data science meetup group, District Data Labs, and she's the adjunct professor at Georgetown, and we're lucky to have her today because I think she's on a plane tonight to go be a keynote speaker tomorrow in Utah at another conference. So let's welcome Rebecca.
Shorter than the other presenters. Hello, welcome to my talk. So I am kind of coming at this from a slightly different perspective than the other presenters and probably many of you in the audience. So really my talk is kind of asking a question. And the question that I would like you to think about and that I've been thinking about is what can you learn from a black box model? So a little bit about me. I'm a kind of practicing data scientist. I work in industry, and really what I do is I build mostly NLP applications. So I'm not a researcher. I did go to grad school, but it was long ago. So now I just do machine learning to sort of like pay the mortgage. So, you know, kind of a different approach to thinking about some of these problems. So what I'm thinking about is sort of coming from that experience of building NLP features, you know, as a kind of practicing data scientist. But my interest is sort of at the intersection of natural language processing-based features in deployed applications and visual diagnostics. So potentially some of you have heard of Yellowbrick. It's a pure Python library, and I'll talk about it a little bit later on in the talk, because I think there is a kind of, it curtails a little bit. So that's really what I would like to kind of think about in this talk, and would like, you know, your ideas and feedback. You know, for those of you in the audience who are not data scientists, or don't kind of self-identify as data scientists, or kind of maybe more on the engineering side, or more on the domain side, kind of, you know, information security specialists, really what data science, I think, sort of boils down to is repurposing data. So kind of taking data that was made for something else, collected for some other purpose, and repurposing it to kind of do something else with. This can get tricky because data science education very rarely touches on issues of privacy and security, maybe almost never. And I feel like I can say that because I teach data science, and so I have I think a fairly good sense of kind of what goes into a lot of the boot camps and, you know, like the master's degree programs. It's, you know, very little sort of thinking about data security, data privacy. You know, increasingly more conversations maybe about ethics and stuff like that, but really hasn't kind of gotten into, you know, really most of the education is sort of like, don't commit your AWS keys to GitHub, please. But, you know, that's sort of where the security conversations usually end. So the problem is that increasingly, I think data science is moving upstream, right? So data science is less and less about kind of analyzing these data sets that are artifacts of some other thing, and more moving upstream into applications. So data scientists playing a role in developing applications and developing features, which means collecting data. And if you don't know how to do that in a way that is sensitive to data security, data privacy, it's very easy to make mistakes, like very, very easy to make mistakes. You know, for example, you know, even if you kind of do things that seem like they solve a problem, like they scrub out like data that you would think would be PII, like social security numbers and names, and you just use some global unique identifier to identify instances in the data set, there is no guarantee that you've actually really done very much at all in terms of securing those people's private information. This data set is kind of just like a example data set. But here's a case where there's no social security number, there's no name. But if you live in a town where there are only 2 Asian American 18-year-old people, you now know that whoever it is you're thinking about is HIV positive, right? Because that's 100% of the population for that subgroup. So that's obviously like a problem. And so these sort of conversations about GDPR and differential privacy are things that I kind of started thinking about maybe 2 years ago. I went to see a talk by Jim Klukar, some of you may know or follow on Twitter. So this is really kind of something that he's thought a lot about, applications, data security, data privacy, differential privacy. I started thinking a lot about this and kind of thinking like, what is the lesson for the field that I work in, which is really kind of, sort of this machine learning, contracting, machine learning as a service, and so one of the examples of kind of when this goes wrong inside an application, is this example of the Strava app that kind of unintentionally, had kind of made all this data private, but kind of released it in order to generate interest in their application, kind of stimulate data science work, and kind of exposed a bunch of army bases and intelligence bases in Africa and the Middle East. And they didn't sort of directly expose it, but they exposed just enough information that it became pretty easy to see that there were outlines in certain places, and maybe the outlines were sometimes roughly airplane shaped, and so that sort of is a kind of a problem when you're an applications developer, because you're not always kind of thinking about what's going to happen. I think that this is particularly scary when it comes to machine learning as a service, which is becoming more and more popular. This idea that there'll be some kind of tool and you turn over your kind of messy, dirty data that's dynamic and delirious, or whatever the other D's were. This data, you put it into this kind of magic thing, and it magics this, this insight for you, and you don't really have to worry about the black box that's sort of taken care of by another company or your contractor or something. They're taking on the responsibility. But that is, a pretty high level, understanding of what a black box kind of in production would look like. In practice, kind of if we think through the steps of what actually goes into that. We've got data, from people or from companies or from documents, and that's used to kind of build a fitted model. And then the fitted model is serialized, right? And it's deployed as an artifact, just like, all of the executables and binaries, that make the rest of the application go. And, a user interacts with the application by providing data about them, in theory, provides data about them, and that data about them is vectorized and sent, into, at the application, sent into, and sent against, kind of like a REST call, let's say, it's sort of sent in as a REST call to the fitted serialized model, which is sort of in the moment maybe reinstantiated and used to generate a prediction and sends the prediction back. That's a big potential vulnerability when you kind of think it through. Particularly, if you're just willing to, like hit the API over and over and over and over and over with your data, other people's data, combinations thereof, maybe using data about people that you do know, whatever data you know about them, and then substituting in hypothetical age, location, stuff like that, and just sending in lots of versions of that, getting back all the predictions, and you end up with a bunch of training data, essentially, right? You end up with these new vectors that have a similar shape to the original training data, and sometimes is so similar that it can expose information, much in the way that we sort of looked at in the differential privacy example. So, I kind of, have done a little bit of light research into this black box model inversion kind of stuff. So, I'm not going to talk a lot in detail about the work that's out there, but I think, these are a couple of the papers that I think are sort of the most interesting, that are worth kind of checking out. The first one here is this Goodfellow paper that essentially found that the more linear the model, the easier it is to invert. And when you kind of think that through, like that seems sort of intuitive. That's not really why people are going in the deep learning kind of direction, like towards less linearity. But it is sort of true that a lot of the machine learning as a service applications and tools are not using neural networks. Most of them are probably logistic regressions or maybe random forests or some combination that does some voting and picks the most performant model. So they're likely to be linear, probably, at least for now, of what's on the market now. The second paper I think is really interesting. It sort of talks about how if you expose any of the metadata around the model, so like prediction probabilities, like I'm predicting that you are like a fan of Taylor Swift with like a 10% confidence interval or something, like any of those kind of metadata things can be used, can help you like reverse engineer the original model. And this is sort of like the third one seems also kind of obvious, but if you are like a machine learning as a service provider and you are making any of the information discoverable about your architecture, that all can obviously be used too to invert the models. And then finally this Song paper, this last one, this is the one that really got me thinking, like, what if you didn't know any of those other things? You didn't know, any of the original training data. You didn't know anything about the, specific kind of model that was used or the architecture or any of that. Can you just start to infer some things from the fitted model, from the kind of the black box? So we're going to kind of like shift now a little bit, because this is a question that I think about constantly, right? Because in my work on Yellowbrick, that's essentially the question is, what can we figure out about this fitted model? How well is it doing? Was there, overfitting happening? Do I need more training instances? How is the kind of bias variance trade-off functioning in this context? So if you don't know about Yellowbrick, I'll just say kind of a few words about it, which is that it's a pure Python library. I started working on it with a colleague of mine, Benjamin Bengfort, about 4 years ago. It came out of trying to teach machine learning to new data scientists who had no background in it, and trying to help them develop some intuition around model selection and model diagnostics. And so the idea behind Yellowbrick is that it's a tool that kind of hooks into the scikit-learn API and wraps those kind of fit, predict, transform methods with visual methods that just really wrap matplotlib plotting routines that probably a lot of people do anyway. So just kind of making those things a little bit easier so that it becomes a more natural part of the workflow. And the idea is that it's supposed to inform steering towards more performant models, right? So to give you kind of these visual indications that your model is becoming more performant or less performant, so it's not a random walk. So just kind of, I don't know how easy it is to see from there, but like this residuals plot, is pretty clearly demonstrating heteroscedasticity, which could be an issue. On the right-hand side, that classification heat map, might suggest potential overfit. So these are kind of, the things that, we're trying to help people develop intuition about. So my question is it possible to use that to kind of anticipate potential model inversion, like attack vectors? So I'm actually not sure, but this is what I've been thinking about, and I wanted to kind of run it up the flagpole and sort of see what you guys think about this. So just a really quick thing, I want to make sure that we're kind of, when I say the word model or fitted model, we're kind of all talking about the same thing. So kind of at the highest level, I'm thinking about model family. So these are kind of groups of models. I'm going to show you some groups of models in a little bit. So these are model families, so they roughly have like kind of a similar architecture, let's say. And then a model form is a specific, a specific kind of version of a model family. So it has a more kind of explicit relationship between the variables, let's say. And then a fitted model is one that's already been trained on data. And so all of the internal parameters have been set. It's been, you called fit on it already, let's say. And so the question is, can you use a fitted model to infer things about family or form? So my first thought is, can you use decision topologies? So potentially you've seen kind of versions of this before. The scikit-learn documentation has a single classifier comparison plot that shows a couple of the common classifiers. But if you actually group the classifiers into their model families, group them into ones that are kind of similar, you quickly see that they have very similar visual signatures, really similar decision topologies when they are sort of, when you collapse the data into a couple of dimensions. So even if these were not labeled, probably you could look at this and instantly say, this is a bunch of linear models. And maybe towards the end, the last couple, something slightly more complex is happening. It can draw circles, so it knows how to do curves, but nothing else knows how to do curves. A simple perceptron can't do curves. So you can kind of sort of see that visual signature. These are trees and ensembles, and it's strikingly similar across all these. These model forms are very different. They behave very differently. AdaBoost and Random Forest are very, very different in practice about how they're working, but the visual signature ends up being really similar. And I sort of call this like a houndstooth. I'm not quite sure what to call it, but that shape that they're all making, where it's these kind of lines and basically anything that does trees or bagging or ensembling tends to have this houndstooth pattern. Nearest neighbor, has an extremely rugged decision topology. It's very striking. It doesn't matter what distance measure you use. You can swap them out, and you kind of get this very similar topology, this sort of visual signature, and it doesn't matter what data you throw at it. It's always going to try to draw these kinds of rugged topologies. And then, even if it's a kernel that you're using, let's say you pick a specific kernel and you throw it into different models, that kernel could be pretty easy to spot. Probably this is another example where even if I covered up the names, you would quickly say, That's an RBF. Because it has that distinctive shape that other kinds of models can't do alone. So what I'm sort of wondering now is this is two-dimensional, somewhat limited. In order to kind of do this in production, you'd have to do a lot of dimensionality reduction maybe, and the signal might not be as clear. But what I'm starting to wonder is if they have these visual signatures, is there a numeric kind of signature that you could also compute? That you could maybe use as just a thumbprint and sort of say, oops, this is one of those models that is pretty easy to find out, and that might be a potential attack vector. And then maybe using that, you could tune your models not to be the most performant, but to be the hardest to invert. So kind of doing things like injecting noise, adding more smoothing, more than's really strictly necessary, so long as it doesn't hurt the performance. If error doesn't increase, maybe smooth a little bit more. Or potentially kind of starting to look at distributions of classes. So are some classes going to be easier to invert than others, using something like multidimensional scaling, let's say. So anyway, some ideas. I'd be delighted to hear your thoughts if you have any suggestions. I think it'd be really interesting to hear what you think. Thank you.
Let's thank our speaker. I think I'd like to start with a question. Maybe it's from you, Rebecca, and maybe the audience, but the question I had is, suppose you could infer the model family. Is anybody aware of a black box attack that would be more effective by knowing that family than just a simple model inversion attack? You get the question? Would that help you in any ways, still not knowing the parameters itself?
So I may be misremembering the paper, but I think that was one of Pepperno's papers when he was talking about basically sort of extracting the model, showed that if you used the right class of model, you needed far fewer samples. So yeah, inferring the model class would actually, I think, be a big boost if you were trying to do some sort of model stealing or capture a model for programming adversarial examples.
Agree.
I have a question. So in the community, they're doing a lot of work on how do you infer a model, infer the parameters, how adversaries, like your talk, right? So I always have these thoughts. So not worry about healthcare. That's not easy. But let's say for a user like me, if I want to obfuscate how Facebook learn about my behavior, what I don't like, what can I do, right? So I think about that question. Now, if Facebook and Google are getting better and better, not letting adversaries to change the way they can predict, does it mean that user like me, it'd be harder for me to mislead Facebook or Google to tell me what I want? So I haven't seen a lot of work on how the user try to click on things purposefully to mislead the social media, right? In a way to inject some data, right? So that they don't learn from us. What's your thought on that?
Yeah, so full disclosure, I've not thought this through before I'm talking, so I'm just going to talk aloud. But what my memory is that when people started, when I was a kid, you would get a bunch of catalogs in the mail, right? And as soon as you ordered one thing from Land's End, the next week there'd be 30 catalogs from a bunch of other places that were similar to Land's End, let's say. And so I think what people started doing is that they would sort of kind of try to invert that deliberately by signing up for things or giving a shell email account to sign up for certain things, or changing the spelling of their name to sign up for certain things, so that you could at least trace where did this probably come from? Okay, Land's End, you're the one who sold my data probably, because now that version of my name that's not really how I spell my name is kind of appearing in all these places. I feel like there must be some kind of approach that's similar to that, where you kind of deliberately perturb things in some kind of maybe even slightly automated way. Maybe you date time is a great way to do that. So when you give your birthday, if you swap the day, year, month around, because nobody can figure out date times, right? So that seems like it'd be a pretty cheap way to do it. That's like one of the hardest problems to solve. Data science has not figured that one out yet.
So as I'm sure oh, you don't hold it down. There we go. I'm sure you're dealing with. What's this slide?
Set of batteries.
Oh, it's out of batteries. I can project, and you can just repeat my question. As I'm sure you're used to dealing with an NLP, there are many ways you can represent a problem. You know, it's not just there's not like one single quantitative representation of a sentence, for example. You know, you could use like counts in a document. You could use word to vec. You could average them. So I'm curious if you've thought at all about like how you could infer like the feature representation being used from a model, or if that's just like totally not something that seems possible to you.
That's a really interesting question. So like in the NLP context, let's say, so you know, there have been times before where at work we were trying to decide, can we use this data set to build something that gets deployed? So for example, if we have a bunch of data about people's IP that's not public, that maybe would potentially expose some stuff that they're still working on and not ready for prime time yet, can we use that data to train a model and then only use that model artifact, you know, and kind of deploy that? And there was at least one case where we realized that like the probability of n-grams co-occurring in single documents could sometimes uniquely identify a specific technology. Because there are some technologies that, you know, are sort of on the fringe or kind of right at the forefront, where, you know, the combination of two n-grams, you know, risked potentially exposing this company's genius idea, and so we decided not to take that approach. So I think it's definitely worth considering.
Yeah, what would happen if you were to build an ensemble of models from various different model families together, some of them linear, some of them nonlinear? Would that tend to make it more robust against these sorts of attacks?
I think that's a really good idea. You know, I think most machine learning as a service offerings, and if anybody kind of works in that industry, like kind of just packaging model selectors, basically, you're welcome to kind of jump in and correct me. But my sense is that's sort of what they do, right? Like they kind of like import all the models, and then they throw the data at them, and then they use a voter, you know, to sort of say this is the one that was best, so pickle that one and deploy it. But I think that generally when that happens, they're not thinking about inversion, they're just thinking about performance. And so I don't think it would be that hard to add some kind of extra layer in that pipeline that says, okay, now backwards, how hard would it be? You know, even a small amount of that I think could potentially be helpful. Like for instance, adding additional, smoothing to something is, you know, something that would be small, but potentially help a lot with, you know, to prevent inversion vulnerability.
Hi, not a question, but more of a comment to what you said. There's actually a talk at Black Hat by Holly Mancharan from Defender ATP team, and she actually talks about how they've used ensembles in order to defeat adversarial ML, and not thinking in terms of performance, but like actually how do you, well, they talk a lot about like how they test their data, and also it's a really good talk, so like kind of like a, I guess like an extension of what you talked about and also your question. Yeah, we're taking a look at. Holly, I don't know how to pronounce her last name. She's from Windows Defender ATP, so yeah.
Yeah, that sounds great. I'll check that out.
Let's thank our speaker one more time. Thank you, Rebecca.
Thank you all.
Well done.